Hello friends, in this session we will be talking about applying state space analysis to electrical circuits. Let's begin. Yes, so for applying state space analysis to some electrical circuit, let us firstly consider an example of a circuit, electrical circuit. Let us say this is a resistance. Let me call it as R1. Let me have another resistance here which is R2. Let me have a capacitor here, let us say C1. Let me have another capacitor here, let us say C2, and yes, that's it, right? Now, and for example, they have already given you in the question that this current is I1, this current is I2, and let us say this current is given to be I3, right? This is R1, R2, this is R1, this is R2, this is C1, capacitor C1, this is capacitor C2, and yes, and let us say the input that is given, that is U, okay? And what are you expected to find is voltage across this resistance R1 plus minus Y. This is the output, because we know that yes, U indicates that input, that U is the input, means for example U may be equal to, let us say, 10 volts, then you may say that yes, U equal to 10 volts. Similarly, if you think of the output variable Y, that also can be taken in the same fashion. Now, so this U is nothing but the input, or we can say input volts in this case, because it is electrical circuit, and this is Y. This Y is nothing but, let us say, output voltage. Output voltage, this is input voltage. Now let us try to apply the same. Yes, now what are you expected to find here? Yes, you are expected to find the output across this resistance R1. This output voltage across this resistance R1 is your Y, right? So now let us start with the solution. See here, yes, now here if you observe, this is C1 and this is capacitor C2. We know that capacitors are energy storage elements, right? And from the previous discussions we have seen that number of energy storage elements, number of energy storage elements is equal to number of states, or we can say number of state variables, right? At the same time, we know one important thing about the states. What is that thing? That they should be at least singly differentiable, singly differentiable, right? That is what we know. So now if you see here, whether those, that particular state, means see here, yes, definitely we have to take either voltage as a state, or we can say I as a state, right? Either you can take voltage as a state, or you can take current as a state. Now whether to choose voltage or to choose this one, current, let us see that. For that, let us go inside the capacitor. See dear, we know that for a capacitor, we know that current IC is equal to CdVc by dt, right? Means if for example this is a capacitor, then voltage across capacitor is Vc, and current flowing through the capacitor is, let us say, IC. So if you see here, this IC, what is the relationship between Vc and IC? That IC is equal to C dVc by dt, right? That is what is there. So now we know that yes, since it is d by dt of Vc, I can replace this as Vc dot. Am I right? Yes. And let me write the remaining things as it is, C into IC. So I can also say that yes. Yes, so now let us assume that this is the node voltage V1, and let me consider that this is node voltage V2. Why? Because see, this node voltage V1, if you see, it is nothing but the voltage across this capacitor, right? Similarly, this node voltage V2, if you see, it is also voltage across this particular capacitor only. And yes, V1 and V2 can be taken as states. Why? Because they are singly differentiable. Singly differentiable in the sense, because we have seen that it is C into Vc dot, right? C into Vc dot. So since it is Vc dot, which means voltages have to be taken as state variables. Voltages has to be taken as state variables in our case, right? So if you see here, yes, definitely you cannot take current, you only need to take voltage here, because they are capacitors, energy storage elements. If they are capacitors and you want it to be singly differentiable, that is IC is equal to V dot into C, right? So that is only possible because this is V dot. V dot is possible means it is V dot, so V has to be the state variables, right? So let us see that. Yes, so now let us apply KCL. Let us apply nodal at voltage V1. Let us try to apply nodal at V1. Nodal in the sense, yes, KCL only, same, right? Already we have studied network theory. So if I apply there, I get C. See here, if I apply nodal over here, what do I get? Yes, this, I get that, yes, definitely V1 minus U divided by this resistance R1 will be this outgoing current, because while applying nodal is what? Nodal is what? Yes, sum of all outgoing currents is equal to 0, right? So if I think of this V1 and this is U, right? So let me consider outgoing current from here, here and here. So if I think of this current, how much is this current? That is going to be V1 minus U, V1 minus U divided by R1. So it is going to be V1 minus U divided by R1. Am I right? Yes. Now plus, because sum of all the outgoing current. So plus sign is taken. Now yes, let us think of this one. How much is this current? This current is given to be I2. This current is given to be I2. So let me consider I2 here. Plus, if you think of, yes, if you think of this current, because this current is done, and now this current is also done. Now let us think of this current. This current is what I see. How much is this current? Yeah, this current is going to be this voltage V1 minus V2 divided by this resistance R2. So plus, so V1 minus V2 divided by R2. This is going to be equal to 0. If you check here, yes, again this V1 minus this voltage V2 divided by this resistance R2, that is going to be the current. Now what about I2, sir? Yes, if you see that, yes, I2 current is equal to what? Yes, I2 current is going to be C1 into V1 dash. How, sir? See, because capacitor current is nothing but what? C into Vc dot, C into Vc dot. So if I am thinking of capacitor C1, if I think of this capacitor C1, then it is going to be what? Yes, definitely capacitor value C multiplied by Vc dot. So it is going to be C1 into V1 dot, because voltage across this capacitor is nothing but V1 only. Voltage across this capacitor is going to be V1 only. See here, voltage across this capacitor is going to be V1 only, right? So yes, now let us simply replace this. So put I2 equal to C1 into V1 dot. So what we get here, yeah, yes, it is going to be V1 minus U upon R1 plus V1 minus V2 upon R2 plus C1 into V1 dash is going to be 0. All the terms are written. Yes, I2 has been replaced by C1 into V1 dot. So now let me call this as equation 1. Now let us apply the same analysis to node V2. Yes, so if I apply the nodal analysis to V2, what do I get? If I just say here this is my V2, right? So outgoing current is this first current and this is going to be the second current. This first current, if you see, is going to be what? This V2 minus V1 divided by R2. So V2 minus V1 divided by R2. Am I right? Plus, yes, this current, if because this current is done, right? So about this current, if you see, it's going to be what? Yes, so if you see here, yes, this V2 which is there, right? V2 is the voltage across this capacitor. So we know that capacitive current is going to be what? I is equal to V dot into C, right? So it is going to be, yes, I3. So current is going to be what? V dot. V dot is going to be V2 dot, V2 dot into C2, V2 dot into C2. So it is going to be I3 which is equal to V2 dot into C2. So let me just write it afterwards. So let me just put, yes, I3 current which is equal to what? Yes, C2 into V2 dot. So V2 minus V1 upon R2 plus, yes, I3 is going to be what? C2 into V2 dot, right, which is equal to 0. So this is going to be equation 2. Now, yes, this was the first equation, right? Yes, from the first equation, if you see, from the first equation, if you just rearrange those terms, if you just simply rearrange the terms of equation 1, you get V1 dot equal to, now this is just simply arrangement. We have just kept this V1 dot here only, and we have just put all of this on the right hand side, and then this C1 has been divided. That's it. So this is how it is done. Now if we just think of this one, let me just rearrange it one more time. So this V1 dot is going to be, yes, 1 by C1 into what? Yes, definitely, because see here, if you just observe here, this V1 and this V1 is actually same, right? Is going to be equal. So let me just take them that way. So if I consider this as U by R1 plus V2 by R2 minus of, yes, 1 by R1 plus 1 by R2 into V1. This is a simple mathematical calculation, right? Let me call this as equation 3. This is the equation that we have got, right? Yes. Now if you see here, rather than this also, if I just make this a bit more good, so let me consider, yes, V1 dot is equal to, let us say, if I just think of this one as, let me just take this 1 by C1 inside. Let me just take this 1 by C1 inside, means multiplying with this will get multiplied by this, and then again get multiplied by this. So if you think of it as going to become, let us say, 1 upon C1 R1 into U plus, yes, when this is multiplied with this, we get 1 by C1 R2 into V2, right? Then again, yes, plus if I do, yes, this will get multiplied, right? So it is going to become, rather, so it is going to become minus the same one, 1 by C1 into 1 by R1 plus 1 by R2. Let me call this equation as equation 3. So rather than keeping this as 3, let me call this equation as equation 3 now, right? Yes. Now let us think of the second equation which we had got. Yes, this was the second equation which we had got. Yes, right. So if I just think of here only, if I do, yes, V2 dot, if I think of V2 dot is going to be how much? Yes, is going to be 1 by C2 into, yes, V2 by R2, V1 by R1 minus V2 by R2. Getting my point, right? Yes, because when this one goes there, definitely this V2 will become minus, and this V2 will become minus, and V1 will become plus. So V1 has become plus and V2 has become minus, and that is how we have got this V2 dot. So if you just think of, yes, let me just write this. V2 dot is equal to, yes, 1 by C2 into R1 into V1 minus, yes, 1 by R2 C2 into V2. Let me call this as, yes, let me call this as now equation 4. So now if you see, I've got this equation 3 and I've got this equation 4. Now let us combine 3 and 4 and let us see what we get. Yes, by the way, yes, we have got this 3 and 4, right? Let us think of output, because we have only got the equations for V1 and for V2. Let us try to understand what will be the equation for the output. Yes, if you think of output Y, see here. Yes, output Y, if you see, this is output Y, voltage across this R1, right? Means this voltage plus minus this voltage. What will be this voltage? Yes, it will be this voltage minus this voltage. So this voltage is U and this voltage is V1. So U minus V1 is going to be Y only, because this voltage, this voltage minus this voltage, that is going to be what? Y. So yes, Y is equal to what? Y is going to be, yes, U minus V1. Let me take this as equation 5, right? Now if I observe from 3, yes, let me just take these equations. If I think of this equation 3, let me take this equation 3 here. Yes, what is that equation? V1 dot is equal to, also if you think of equation 4, which is for V2 dot, V2 dot is 1 by C2 R1 V1. This is what was the equation 4. And if you think of this output Y is how much? Yes, U minus V1. Now just see here, this is what is very important now. Now if I want to show all the these three equations in terms of a matrix, how will I show? Now you please tell me here. See, we know that, yes, x dot is equal to ax plus b, bu, and we know that y is equal to cx plus du, right? Yes, but if you see here, yes, now we have taken states. This x is nothing but states, right? And states in our case are nothing but v1 and v2. So in place of this x, what we will write? We will be writing v1 v2 vectors, right? Now in place of this x dot, yes, definitely it is going to be v1 dot and v2 dot, right? And this u is going to be u only, and this x also same. Here we will be writing v1 v2, and this is going to be y. So if I try to show these same equations, if I try to show in terms of matrix, I will see to them as follows. So we have v1 dot and v2 dot, right, which has to be there, v1 dot, and because if this equation, if I think of only this equation, then yes, definitely this x dot, this was x dot, so x dot is nothing but v1 dot and v2 dot, right? So this is going to be v1 dot and v2 dot equation we have to consider. So yes, if you see here, definitely what we have is, yes, by the way, here we have v1, in the equation. Anyways, yeah, it's okay, no problem, because see here, yes, here also we had this v1, no, we did not write this v1 here. Yes, so that is what was there. Anyways, now if you just see here, v1 and v2 are written, no problem. See, I just need to show them in terms of matrices, that's it. Now if I take v1 and v2, because this x has to be written, right? So let me take this v1 and v2, right? Now inside this, here what elements will come here in a, what elements will come, let us see. If you think of this v1 dash is going to be what? Yes, if you think of this v1, this is going to be the coefficient with v1, minus 1 by C1 into 1 by R1 plus 1 by R2. This is the coefficient. Alright, so let me just show this equation with V1. So yes, if V1 is shown here, then definitely that is going to come here. So it is going to be, yes, minus of 1 by R1 plus 1 by R2 into 1 by C1. That is what is there. This is written. Now if I think of what is there with V2 here, what is there with V2 here? Yes, with V2 we have 1 by C1 R2, 1 by C1 R2. So yes, definitely plus 1 by, because this is V2, right? So this has to come here. So it is going to be 1 by C1 R2, 1 by C1 R2, 1 by C1 R2 is written here. Now, if you think of V2 dash, yes, if we think of V2 dash, yes, see here, with V2 dash, if you see, with V1 what we have is, yes, 1 by C2 R1. So 1 by C2 R1 will come here, right? Yes. Now after that, if you think of, yes, what is there with V2 here? What is there with V2? Yes, definitely we have minus 1 by R2 C2. So minus 1 by R2 C2, because we know that, yes, metric multiplication happens in row by column way, means this first element will multiply with this element, then again this element will get multiplied with this element, right? Right, and then again, yes, this will get multiplied with this, and then again this will multiplied with this. So in this way, at the end, the same equation, these same equations will be got. Now let us think of output equation y. Output equation y is, yes, u minus v1. So if you think of output equation y, right? Yes, definitely here, yes, here it was x, it is cx, it is cx, no, so this is cx, and x, in place of x you have to write v1 v2. So it is going to be v1 v2 vectors, v1 v2 voltages, right? So here what will you have? Yes, see here now, y is equal to, yes, u minus v1, y is equal to u minus v1. So with v1 what you have is minus 1, with v1 what you have is minus 1. So here you are going to have minus 1. Do you have any term related to v2 here? No. So here if you see, v2 is going to be 0. Then yes, definitely you have this u, right? You have this u, right? So this is going to be plus 1 into u. So this becomes your state space model, which we have derived from, yes, we have derived this from a electrical circuit. This particular state space model has been derived. Now what do we observe here? What do we observe here? That is going to be very, very important. If you see, yes, all these parameters, what, r1, r2, c1, c2, all these parameters which were there inside the circuit are shown in matrix A. In matrix A, if you see, this is matrix A, right? This is matrix A. So in matrix A, all these parameters, all these system parameters are shown in matrix A. Yes. Now another important thing which we observe from this one is that the output of capacitor voltage C1, if you see, yes, the output is y, right? This output is y. If you see, yes, y is equal to minus v1, minus v1, right? Minus of v1. And if you see this v1, v1 is what here? Yes, v1 is going to be the voltage across capacitor c1, capacitor c1, voltage across capacitor c1. So by this state equation we have understood that, yes, output is dependent on voltage across capacitor c1. Just imagine if we had only this transfer function approach, what we would have understood? We would have only got this y of s upon u of s, that's it. We would have never understood that, yes, this y of s is also dependent on capacitor voltage v1, right? But now here with this state space model we have understood that, yes, this y of s, or this our output y, or output y of t, output y is dependent on voltage v1, which is nothing but the voltage across capacitor c1. Now just imagine, this is what is important, this is what we think of, yes, hidden parameters. See here, if for example this capacitor c is burnt, if for example this capacitor c is burnt, you will be saying, sir, what has happened then? Yes, if this capacitor C1 is 1, then definitely V1 is going to be 0, and if V1 is going to be 0, then this output Y is going to be 0. Now just imagine you don't have this state space model. You don't have this state space model. You only have this transfer function. Then you will never be able to troubleshoot the problem. You will never understand that yes, this output was dependent on capacitor voltage, but you don't know that. Why? Because in transfer function you only know this y of s upon u of s, y of s upon u of s. So you will never understand that yes, this output voltage of the circuit of that particular R1 is also dependent on capacitor voltage, which we have understood from the state space model. Otherwise we would have not been able to understand it. So yes, now you may ask me, sir, but it's okay. No, yes, if the capacitor gets burnt, it's okay. How is that okay? No, because V1 is equal to 0, because if capacitor is burnt, then yes, voltage across that capacitor will become 0 and output will become 0, and you will not be able to troubleshoot the system just by looking at the transfer function. Let's say if you don't have any other information apart from the transfer function, then you will not understand that why my output is equal to 0. Everything is okay, but still why my output is 0. But yes, if you have the state space model, you will definitely understand that yes, since it is dependent on capacitor voltage, the capacitor might have burnt out. That is the reason why my output is 0. Anyways, so this whole equation, this whole is called as the state space model, and it has been derived from a electrical circuit. Thank you.